Okay, so we have covered finished two sections. One is address management, and another section is on error control. I mean error reporting, not error control, error reporting. And the next two sections will be on routing, unicast routing, and multicast routing. We have homework number 4 on chapter 4. There'll be 3 hands-on and 8 written. And it deals 2 weeks away from now. That's December 1st in the class. So next, let's look at routing, unicast routing and multicast routing. And again, we have mentioned that IP multicast routing is not a successful technology. That because it changed the stateless nature of the routers. It would change the stateless nature of the router. So it's difficult to deploy and difficult to scale. So IP multicast is only used in a limited scale on the local area networks. So in a local domain, so for example in NCTU, we use a multicast, IP multicast, for some live sport event, so, but only on campus, on certain subnets, not on all subnets, but only on certain subnets that support IP multicast. Instead, people are looking at application layer multicast. That's done by multicast servers at application layers, not at IP layer. So we would, but we still want to talk about multicast routing to give you an idea how it works, but it doesn't quite succeed, and you need to know why. But for unicast, it does not destroy the stateless nature of the routers, so it is of course quite successful. So we look at the unicast routing first, and we look at the principle, and then look at the intra-domain routing by RIP and OSPF, 2 routing protocol, and then inter-domain routing by BGP. Okay, so we would talk about 3 protocols, 3 commonly used protocols here. But first of all, let's look at the principle. And in the principle, we need to look at 2 routing principles. One is link state routing. The other is distance vector routing. But before that, let's see what is routing. And we have talked about that in chapter 1. The test of routing is actually to select a path to the destination. And the way that IP router interpret this is to calculate, to compute the next hop, for a packet. To compute the next hop for packets destined to a destination host. So this selecting a path is actually to compute the next hop. Okay, in the interpretation by the IP routers, IP routing. Okay, and the goal of routing is to be efficient and scalable, stable, robust, and fair in forwarding a packet. So you want to be efficient and all these features in forwarding a packet. And because of this principle of optimality of IP routing, we could use a hub-by-hub routing instead of end-to-end routing. So this is the way you interpret this. If we use a hub-by-hub routing, and every router determines its own routing table, Y packet will be delivered to other destinations along the optimal path. So the problem can be restated as this. From S to D. So S is the source and D is the destination, and K is the intermediate node, most likely a router. K is the intermediate node on the optimal path. So if K is in the intermediate node on the optimal path from S to D, so this suppose this path is the optimal path from S to D, and K happens to be on the optimal path. Then the principle of optimality of IP routing says that this path is also the optimal path from S to K. And this path is also the optimal path from K to D. That is so if we have another path here, another path here, suppose we say this is a S and D, this path is the optimal path from S to D, and K happens to be on the path. And if we say this path is not the optimal path from S to K, and this path is, this is the optimal path, but this is not for the path from S to K, then we can prove by contradiction that if this is the optimal path, then I would take this as this path. And if this is optimal path from K to D, I would take this too, and then form an optimal path from S to D. Okay, so that is essentially proved by contradiction, would tell us that if the path has been an optimal path, then it will be an optimal path from S to that. I mean, each piece, each segment of the path will be the optimal path. So if this is optimal path, then this is optimal path from S to K, and this is optimal path from S to D. And so this is suppose this is J, and this will be optimal path from K to J, and this will be optimal path from J to D. So that is the property of this optimality. So it says that a shortest path tree can be constructed from a source to the rest of the path. So if I have this optimal path from to span to many other destinations, then I would form a spanning tree, a shortest path spanning tree that will span to many nodes. Okay. Okay. In saying that, if you do every router compute the next hop, the next hop along the to a destination, then you would form a shortest path tree, and this hub by hub routing would work. You don't need to compute the entire path. I mean the shortest path. You just compute the next hop that would lead to the shortest path. So essentially, this proves that the hop-by-hop routing will be good in finding the shortest path. Okay. But how do we do hop-by-hop routing to find out the next hop in the shortest path? We can base on either global information or local information or decentralized information, global or decentralized information. If we have global information, it means, I mean, the global information of the domain of a network. So within this room, if each of us is a router, and if each of us broadcast within a network, within this network, our link state information. By link state information, it says that if I have 3 neighbors, 1, 2, and 3, I have 3 neighbors, then I would broadcast I have 3 links. I will broadcast the link state to the entire network. So I'm saying to every one of you who are my neighbors, and the link state, say the delay on this link, on these links. So I'm broadcasting the link state to every one of you, and every one of you does the same thing, meaning broadcast your link state to every one of us. Then we would be able to construct a topology of the network. Suppose each one of us send the link state, broadcast link state. So I have the link state of each one of you, so I know who are your neighbors, and also I know your delay to the neighbors. So I will be able to construct a topology whose neighbor, and so that will be a topology, a graph. And also I know the delay on each link, right? That's the link state. I know the delay on each link, so that'll be the cost of the link. So then I will be able to use the Dijkstra algorithm, to compute the shortest path. Actually, the shortest path tree. I can compute with Dijkstra. Within the topology, I can compute the shortest path from myself to the others. So I can compute with Dijkstra algorithm. We'll see how Dijkstra works. So with Dijkstra algorithm, we would be able to construct the shortest path spanning tree. And from that spanning tree, I transform it into my routing table. So each one of you would do the same. You will broadcast, and then you will construct the topology. And because it's a broadcast, the topology I got will be the same as the one you got. You also get the same topology. Then I compute the Dijkstra and put me as a source. So I will compute the shortest path from me, and also you can compute your shortest path from you. So everyone do the same. Then you got your routing table. I got my routing table, and which are consistent because the topology we use are the same. That's link state routing. How about and that's based on global information. How about decentralized information? That's done by the so-called distant vector routing. And what is distant vector what is the difference between distant vector and link state? With link state, I only know who are my neighbor and my delay to the neighbors. Okay, but for distant vector, I know the destination. I mean, for each destination, I have an entry in my distant vector. And here's how. Suppose we don't want to broadcast. We just want to exchange with neighbors. We exchange with neighbors about things we know, but we don't want to broadcast. So I tell my neighbor, okay, so my neighbors know me now. I talk to my neighbor. I have 3 neighbors. I talk to them, so they know me now. They know my ID, and also they know the distance to me, and also the neighbors talk to me, so I know each of them. So my neighbors know me, and I know my neighbors, and also I know my delay to the delay to my neighbors. However, since this neighbor know me and also know the delay to me, but it also exchange this information with his neighbors. Suppose he has 3 neighbors. Okay, he also tell the neighbor, and it put the things it knows into the distance vector. Suppose he know 3 things or 2 things, it would tell the neighbor that suppose he has 5 neighbors, for example, me and the other 4 guys. So what happened is that it would tell the other 4 about me. So these 4, they would know that this neighbor can reach this guy with a delay of that. And the delay that he can reach me will be the delay from him to him plus the delay from him to me. So because my neighbor tell his neighbor, so his neighbor will know me, and also his neighbor will know if he reach me through this neighbor, the delay will be this plus this. Okay, so by just exchanging the distance vector, the other guy over there at the very end, it would know me eventually in several iterations, and then he would know how to reach me. Suppose that guy tell him that he can reach this guy, and then this guy, and then this guy. He would tell him the distance vector. Okay. So without broadcasting, by just talking with neighbor, exchanging with neighbor about things you know, we will be able to know all of us. Same to me, I would be able to know from my neighbor. Eventually I would know him, and I would know to reach him. I can send it to this guy with a delay of what. So without broadcasting, by just a neighbor exchange, we will be able to compute the shortest path. And that algorithm is called Bellman-Ford algorithm. And we will see an example. So now the difference is clear that link state is about, suppose I have 3 neighbors, then I would have 3 links. So I would have 3 pieces of link state. However, with the network, if we have 20 routers in this room, in this network, then I would have a distance vector with 20 entries, right? With 20 entries. So from destination 1 to 20, I know their distance. So the link state is about the neighbors only. I mean the links I have. If I have 3 neighbors, I would have 3 links. I would have 3 link state information. But for distance vector, if I have known 20 neighbors, including myself, then in my distance vector, I would have 20 entries. And I would tell my neighbor about things I know. I don't broadcast the distance vector, but I do broadcast the link state. Okay. And that's the information which is based on either global or decentralized information. And how do we collect and compute the routing table? Could it be static or dynamic? Static means that the routing table is fixed. It's not and it's once computed, once configured, it's fixed. Dynamic means that routing table would adapt to the network status. And of course, we want to be dynamic because the network condition changes. So when there's a congestion, I might want to change the route. So the routing table needs to be dynamic. So so we would not consider this, of course. This is rule out. It's got to be dynamic. But for the information you use, it could be global or decentralized. And the way to compute the path, to compute the shortest path, is to view a network as a graph where nodes are routers, but links or edges are physical link. And associated with a link, there's a cost. And the cost could be delay or congestion level or something else. But in the internet, the cost is usually the delay. And then you want to find the shortest path, which will be equivalent to the least cost path, the path with the least cost. Okay, let's look at the link state routing first, which is based on global information. And we need to do it we need to collect the global information by reliable broadcasting. And you will see that this is done by OSPF, and OSPF right on top of TCP. And the reason it right on top of TCP is because it needs to do reliable broadcasting. You need to send the link state to all routers reliably. And of course, it's dynamic. You dynamic update the routing table. And the calculation is done by Dijkstra. So let's look at how Dijkstra works. Before I look at this, before I explain this, we look at an example. So if by broadcasting the link state, if every router broadcasts the link state, then every router will get the same path and the same figure, right? The same topology of this. So every one of these 5 routers will get the same topology if they broadcast the link state. Each of them broadcast the link state, and they got the same figure. Now I'm router A, so I want to compute my routing table. I mean the routing table for router A. If I'm router E, I will compute the routing table from the aspect of routing E. So this is the end result. We got a routing table for router A. So it will compute for destination B, C, D, E. But again, if I am router E, I will compute a routing table destined with destination to A, B, C, D. But now consider I am router A. I want to do the computation. I want to compute to get this for myself. So what would I do? By Dijkstra, it says that, first of all, you, from A, because that's the source, you try to label your neighbors. So I label my neighbors. For neighbor B, I label 4 because I can reach B in one hop with a cost of 4. And that's because I can reach B directly, so that's through A. And I label C with 1, and also I can reach C directly. And then and then nothing else. I cannot label D and E now because in the first iteration I only know I start from myself. So first of all, I mark myself. I mark A, which is myself, and I label my neighbors, which are B and C, and with the label 4 and 1. Secondly, in the next iteration, from the nodes which are labeled but not yet marked, Okay, so I have two nodes which are labeled but not yet marked. I pick the one with the shortest label, with the smallest label. That will be C. So C, I pick C, I put it into the set T. Now I mark C because it has the smallest label. So I pick C to mark. I mark C. And now from C, I try to label the others. Okay. I find out that I can relabel B because of what? I can reach B in a distance of 1 plus 2. That would be 3. And 3 is smaller than its original label, 4, which is from A. So I can reach B in a distance of 3. So I relabel it immediately. And that's through C. So in a sense that A will reach B through C. And the distance is only 3, which is smaller than if A reach B directly. So if A reach B directly, the distance is longer as 4. But through C, the distance will be small. The cost will be just 3. So I relabel it. And then I try to relabel D and E. So I relabel D. 1 plus 3, that will be 4. 1 plus 1, that will be 2. Okay, that's the end of the second iteration. And then the next iteration, from the nodes which are labeled but not yet marked, I pick the one with the smallest label and I mark it. So A and C have been marked. They have been marked. So from B, D, E, I pick the one with the smallest label. Which one have the smallest label? This one. So I pick E. I put E into the set. I mark E. And then I try to relabel. Okay, can I label D? Yes. Then D, the label was 4, but 2 plus 1 will be 3. So I relabel D from 4 to 3. So D has been relabeled. And that's the only thing I can label from E. Okay, that's done. So the next iteration will be I pick. Now I have A, C, E. I pick among B and D, which has the smallest label. There's a tie. So B and D have the same label. So I pick B. Okay, I pick B. And so I mark B. And then try to see if I can relabel relabel D. Can I? No. Either through no, I cannot provide a better path. So I cannot relabel D. So that's done. And then D is the only node left which are labeled but not marked. So I mark D. So now with this, I now got what? I'm A. I can reach B through C with a cost of 3. I can reach C through A with a cost of 1. I can reach D through E with a cost of 3. I can reach E through C with a cost of 2. So I will take that information and then put it into a routing table. To reach B, I go through C. So to reach B, I go through C with a cost of 3. To reach C, I go through A with a cost of 1. I can reach, well, to reach C, the cost is 1, and the next hop is C because it's direct. to reach to reach D, that's through C. Yeah, the next hop is C. To reach E, that's also through C with a cost of 2. So I got my routing table from this. I do the computation for myself and take me A as the source. So everyone got the same topology, but they compute for themselves. So they got different routing table, but the information should be consistent. And I compute myself my routing table for node A. If it's a router B, it will compute from with the source from B. So that's diastra. And if we take this the example, we go through this. So initially, there's only the source is in the set T. So we get into the while loop until T is equal to V. If T is equal to V, then the while loop ends. Otherwise, we do this. V is the original set. Every router in the set. So what it does is find out W, not yet marked, but has a label. And the label, the cost of W, which is a label, is the minimum for all node, for all W, not in T, not yet in T. So that's what not yet marked, but labeled yet, labeled already. And I want to pick the one with the smallest label. I will find out that particular node, and then I pick that one into the mark set, the set of mark. I mean into T. So I'll mark W. So W is the one with the smallest label, but not yet marked. I would mark W, and then after I mark W, then I do what? I try to relabel. I try to relabel for each node which are not yet marked. I try to see whether I can provide a better path. If I can provide a better path, I mean my cost from the source. This is the cost. I mean the distance from the source to W, and plus the cost from W to V. If this is shorter, then I replace it. If this is shorter than this V, then I relabel it. So I'll pick the minimum. And then PV is the, if I relabel, then I become the next hub, the previous one. Okay. So this is essentially what we have run through. In each iteration, we first mark the one with the smallest label, the one with the one which is not marked but with the smallest label. So then we mark it, and then once we mark it, we try to relabel its neighbors. Okay, so that's a Dijkstra algorithm which is used in link state routing. How about distance vector? The distance vector is a local, rely on, it uses the local information only. So only local information is known. It knows the status of adjacent links and routing information of adjacent node. And but I can add up things that my neighbors told me. My neighbor would tell me something it knows, so I add up this information into things I know. So I would know more and more. And this dynamic the same. And the calculation is done by a Bellman-4, the Bellman-4 algorithm. So let's go through this. Here again, this is an algorithm, but let's look at the example first. See, this is well. So now we don't have this topology in the router. We don't. In the Bellman-4 algorithm, we don't have this topology. We only have this. Say if I'm A, I only know this. I know B and C and the cost to B and C. And the next hop to B and C will be B and C. Okay, I know, initially I only know this. I don't have the topology, so I'm drawing the topology just show you the whole thing, but as a router A, I don't have the topology. I only know my neighbors, okay. Unlike Dastra, I know the topology. Every router knows the topology. But in Bellman-4, I don't have the topology. I only know this. And every router only know partial information. They only know their neighbors in the beginning. But see, this is supposed to be okay. So C know, because C has more neighbors, right? So C have A, B, D. Everyone is C's neighbor. So C knows A, B, D, E. He knows everything. I mean, he knows all the other neighbors. And it has the cost and also the next hop. So now, starting from this, what would happen next? So initially, I only know B and C. But C knows B, D, A, B, C, D, A, B, D, E. So if C take this out and into a thing called distance vector. So this is actually a vector, and it takes this out, and then send this distance vector to me. And B does the same thing. So what happened in the second iteration will be this. I would know, initially I only know B and C, right? Now I know D and E because B and C told me about it, told me about D and E. And even for B and C, I change things I know. For example, here I know C, I can reach B. I can reach C with the cost of 1, and the next hop is C. But now, since C told me that it can reach B in a cost of 2, so add up with this and 1, cost of 1. So I know the cost to reach B through C will be 3, which is better than mine. Than things I know initially. So I changed to B. I will go through C instead of to B directly, and the cost will become 3. So I changed because of things told from by C. And also for D and E, I know C and B gave me something, and I would compare them. Initially, I would know. Eventually, I would know that if I want to reach D, I should go through C, because C provide me a better path, which is with the cost of 4. But the path provided by B is longer with the cost of 5. To E, the same. C told me that I can reach E with the cost of 1. And I can reach C with the cost of 1, so the total cost will be 2. And B does not tell me about E, because E is not the neighbor of B initially. So initially, B would not. So in the second iteration, I know E because of C. So from this, we will be able to, and then the next thing is that we change this. So see, So you watch this. Initially, I think I can reach D through C, right? Through C and in this way. But then because C has realized that it can reach D through E with a cost of 2. So that information is propagated to me. So my next hop will be saying, in the next iteration, I would change my mind. I would change to a cost of 3. But it's still through C. And eventually I got this, and this is what? My routing table. So this is exactly the same. See, this is exactly the same as this. As this. Okay. So I still compute my routing table. I got this. And this is the same as this. This. So either through Bellman-4 or Dijkstra, it should get the same result for the same network. But the way they compute this is totally different. It's totally different. And so now we got this, but if we look at the algorithm, here's the algorithm. It says that what we just run through is this. So if I'm X, I receive the distance vector or the so-called route update message from Y. If I'm X, I receive a distance vector from Y. And within Y's report, I will take the pair, this destination distance pair, which is a distance vector entry. I will check if if the destination is new, it means that I haven't seen this. This is new to me. Then I would just take it. If the router, if my neighbor router, my neighbor is Y. If Y is telling me something I never know, someone I never know, I would just take that information. I will add a new entry in my table, my routing table. Say, okay, to this destination, the distance will be the distance that told by my neighbor. My neighbor told me this, but I need to add up with the distance from me to my neighbor. Okay, and the next hop will be my neighbor, for sure. Okay, so if my neighbor is telling me some router I never know, I would add up. But if my neighbor is telling some route, some destination that I have known, then I need to check whether my neighbor is providing me a better path. If my neighbor Y is providing me a better path, I would change. If my neighbor is not providing me a better path, I would ignore. So I check this. If the distance provided from my neighbor to that destination plus my distance to the distance to my neighbor is smaller than the distance in my routing table for this destination, that means if this is smaller, that means my neighbor is providing me a better path or a worse path. Better. Worse. If you think this is better path, raise your hand. Worse path, raise your hand. Okay, you're not sleeping, so good. So that means my neighbor is providing me a better path. Oh, I wrote it here. Okay, so then I do what? I switch. So then I changed. The distance should be the shorter one, and the next hop should be my neighbor. I change it. If it's larger or the same, then I don't change. Periodically, I would if I have updated my routing table, I would do what? I need to tell my neighbor right now, or periodically. So if my distance vector has been changed a lot, it's better that I tell my neighbors as soon as possible, so that I can propagate the network change sooner. Okay, or I can, if the change is not much, then I would wait until the next exchange. So I might exchange with my neighbor. I would exchange by my neighbor periodically. Usually the timer is set to 30 seconds. So every 30 seconds, we exchange distance vectors, and then we will compute. We update the routing table. So this is a Bellman-Ford used to compute this. Okay. So with the distance vector, with the with the link state, we use Dijkstra algorithm. With the distance vector, we use Bellman-Ford algorithm. Okay. We got the same routing table, but the way they compute is different. But we will see then either one is fine. No. The Bellman-Ford algorithm is more scalable. However, the Dijkstra algorithm is less scalable. Just think about this. It's the complexity is of this algorithm is n squared. If n is the number of node, it will be n squared. But in the Dijkstra, it's n log. I think it's n log n. So the compressor is lower in that Bellman-Ford, but higher in Dijkstra. You can look at the complexity to compare them, and you can also compare them with one thing. Is the Dijkstra algorithm? You need to have the topology, the whole topology, before you can compute. And consider a network with 1,000 routers. Then the topology will be huge. So if the network is large, then you consider a network with 1,000 nodes. Then the topology is too large to compute. It would take a much longer time to compute, given that the complexity is n squared. Okay, but with the Dijkstra, with the Bellman-Ford algorithm, you don't need a topology. You don't need a topology to compute. You just got distance vector from your neighbors. Okay, so Bellman-Ford is more scalable, that can scale to a large network, but Dijkstra cannot. Then you would say, then why not we just use Bellman-Ford, ignore Dijkstra? Don't use Dijkstra, just use Bellman-Ford because it's more scalable. Of course, there's one disadvantage of Bellman-Ford, which is slower to converge. It's slower to converge. As you can see, we need to wait. See, in this configuration, you need to wait until they exchange distance vectors. So the first time I got this, and the next time we exchange distance vector will be 30 seconds later. So if I need three iterations to converge, then that means that I need 90 seconds to converge, right? I need 90 seconds to converge my routing table. And this is only a small network. If this is a network with a diameter of 10, what is a network with diameter of 10? Consider a network that pick any two nodes to see in how many hops they can reach each other. If the diameter of 10, it means that the pair with the longest, shortest path is 10. I mean, there's a pair in this network with a shortest path of 10. That means the diameter is 10. So consider it's a small room, and we only have 25 people here, and I have neighbors 3. And in order to reach the farthest one from me, I probably need 1, 2, 3, 4, probably 4 or 5 hops. Then the diameter will be, if it's 5, then the diameter is 5. Okay, but consider if it's 5, then it means that every 30 seconds we exchange distance vector, and so the information of me will be propagated to you in one iteration. That will be 30 seconds, and then 30 seconds later it will be propagated to him, so that'll be 60 seconds already, and then next hop will propagate to him, another 30 seconds. So that means that 150 seconds later, that guy over there would know me and would know how to reach me. So it takes too long to converge. And if we have some congestion here, maybe there's serious congestion here, but there's no congestion. So I probably can reach him through this. So the path needs to be flapped, right? The path needs to be switched from this to that, because we have congestion here. Then how long will that happen? Probably 150 seconds, because the information needs to be propagated. So that means the routing path will be changed 150 seconds later, after the congestion has been detected. Okay, after we change the link cost. So that's very slow. So it takes too long to converge, which is the major disadvantage of the Bellman-4 algorithm, or the distance vector routing algorithm. But with Dijkstra, with the link state routing, if I have some update, I broadcast my link state to all the routers in the network. And if we say that broadcasting is done by the link state information broadcasting is done also in 30 seconds period. Every 30 seconds we broadcast link state. Then the problem will be broadcasted, and everyone know that there's a congestion. The link state has been increased. The link cost has been increased. Then everyone will recompute. So within 30 seconds later, we would change the path to a better one. So immediately you see that if there's a congestion, the Bellman-4 algorithm needs to take, in this example, 150 seconds to converge and then change the path. However, in Dijkstra, it will be just 30 seconds to change the path. So the reaction to congestion will be totally different. So we see the advantage of Dijkstra, although it's not that scalable. There's another problem with distance vector. In addition to the so-called longer time to converge, it has another problem. It says that the phenomenon is this: good news travel fast, bad news travel slowly. So in this particular topology, this is fine, but the problem happened here. If this within this network, if this link cost is high, but this is small, but there's a congestion, or the link is broken, it has link failure, So it becomes infinity. What happened is that sorry, it should be the original one should be this. Remember, to reach B, we thought we can reach C. We can go through C to reach B. And sorry. That's good news, travel fast. So for example, it was 7. If I change the link cost become smaller to 1, then I will switch from B to C. So I will switch quickly. The routes update will be done in 2 iterations. But if this configuration, if this is high and this is small, but this link become failed, if the link failed, then it would take a longer time to realize because I go through C to reach E, B, and D. But since this cost is too high, I would insist to use C. For example, if I will continue to go through C because this link cost is too high. There's a configuration. There's a scenario explained in the text that would make A to think that it can use C continuously because the cost to B is too high. And it would change after 25 iterations to realize that B is a better path. B is a better path. So the bad news travels slowly in this scenario, and the procedure is described in the text. You can read that. So the problem is this, and there are solutions, partial solutions for that, the so-called count to infinity. This problem is called count to infinity. You count to infinity. And there are 3 solutions. One is split horizon, and then second one is Poisson reverse and hold down timer. It all says that you need to be careful about things told from your neighbor. So for example, in the split horizon, it says that the routing update sent to a neighbor should not contain routes learned from that neighbor. If I'm sending a distance vector to a neighbor, I should take out. It should not contain the things I learned from him. If I send things I learned from him also to him, there'll be a recursive problem. I only tell things I learned from somebody else, but I don't tell him things I learned from him. So that's called split horizon. And Poisson reverse is similar. It says that if A learns a route to D from B, then A tells B that it cannot reach D so as to poison the route. Okay, it says that if I'm A, I learn a route from B to D, and I tell B that I cannot reach D. Okay, so if I'm using for destination D, if I'm using B as the next hub, then in the information, I should not tell B I can reach D. I should tell B that I cannot reach D. So that's called Poisson reverse. Otherwise, B will think that if B has some link failure, it will think that A can provide a better path to D. B will think that A can provide a better path to D if the link from B has failed. Okay, so I think I know this might confuse some of you, but for the detail, please, or the scenario, please read the book. Okay, so the problem happens when it tells us that you should not take information that you learn from your neighbors and utilize and feed it back to your neighbors. No. Okay. Okay, so the counter infinity problem can be partially solved in distance vector, but the slow convergence cannot be solved. It's still slow. That's the disadvantage. So for a small network, fine. But for a large network, it takes a longer time to converge. But actually, you will see that distance vector is actually used in the backbone internet. In the internet backbone, we use this. And it's indeed, it takes a longer time to converge. I mean, the backbone in the routing table in the backbone router would take a longer time to converge because of it used distance vector. But can we use because of the slow convergence, can we give up distance vector and use a Dijkstra algorithm in the backbone routers? No, you better not, because the backbone router is too large to fit to be calculated by Dijkstra. So you don't want to do that. So you want to stay with distance vector for the backbone routing. Okay, but since the internet is so large, you don't want to do the routing. You don't want to treat the internet as a single router, a single network. You better divide it into domains. So what we did is that it's not a freight network, it's a hierarchical network. If it's freight, there'll be too many entries in the routing tables. So then you define domains. And we have seen that, so you have, from the bottom, you have subnet, and then top, you have domains. And routers within a domain are under the same administrative control. For example, this campus is a domain. And an ISP network is a domain. And routing within domain and between domain can be done separately. So within NCTU, within the campus, it does its routing. It can decide whether it wants to use Bellman 4 or Dijkstra algorithm, or in a sense, RIP or OSPF. And in the backbone, it's an inter-domain routing problem. So the backbone router, they need to agree on what routing protocol they would use. And they agree on one thing, which is BGP. And BGP runs Bellman 4 algorithm, which is scalable, although it's slower. It's slow to converge. So a domain is called AS, which is autonomous systems. And AS could be stop AS or multi-home AS or transit AS. The difference is transit AS is usually an ISP. An ISP usually is a transit AS. But a campus or so for example, NCTU is a multi-home AS because we connect to several domains, several ISP. Stop AS is usually for a small enterprise. two-level routing, inter-domain, intra-domain or inter-AS, inter-domain or inter-AS. So in this figure, you see, well, this the background is not shown. I don't know why. Perhaps the color is not dark enough. But in my slide, it shows that here are 3 domains: domain A, domain B here, and then domain C. So domain A and C are stop AS, stop domain, meaning that they have only one entry. Okay, but domain B is multi-homed, so it got 2 routers connected to the outside world. Okay, so so now these four they would run. They are inter-domain routers, so they will run the inter-domain routing jointly. These 4, but this within domain A, these 3 routers together, they will run what? Intra-domain routing. Intra-domain routing here. So you run intra-domain routing here, intra-domain routing here, intra-domain routing here, but inter-domain routing here. And intra-domain routing, they would use, you could pick RIP or OSPF. Intra-domain routing, you could pick BGP. For intra-domain routing, if you pick RIP, then you are running Bellman 4 algorithm. If you pick OSPF, it runs Dijkstra algorithm. And because within a domain, the number of routers is not too many. So you either pick Dijkstra or Bellman 4. It doesn't matter that much. But for inter-domain routing, because within the backbone there are tens of thousands of routers and domains, tens of thousands of domains and routers. So the number of routers will be too many. If you run Dijkstra, it won't be scalable. So you need to run Bellman 4. So BGP runs Bellman 4 algorithm. It doesn't run Dijkstra. So that's the reason why in the inter-domain routing we only have one protocol. I mean, we only use Bellman 4. We don't use Dijkstra. That's the reason why it won't scale. Okay, then given that we have known the idea of the Dijkstra and Bellman 4, or the distance vector and link state routing, so we can look at the protocol aspect, RIP and OSPF. And RIP is the oldest routing protocol, and it runs distance vector, and it uses hop count as the cost. So the cost will be, and it defines the cost can be up to 15, meaning that within the domain, the network diameter is 15 at most. 15 at most. So it put a limit, the network size to 50 within 15. I should say the diameter, not the size, not the number of routers, but the diameter of the network. And it exchange routing message, which are the distance vectors, every 30 seconds. That's the default value. You can change that to exchange more often, but the default is 30 seconds. And each distance vector could be could advertise at most 25 routes. 25 routes. So that's the length of the distance vector. It's at most 25. If you got more than 25, then you send it into 2. You need to split into 2 advertisements or 2 links, 2 distance vectors. So each vector the length of a vector will be 25 at most. So it looks like this, the protocol messages. So that'll be 1. If I have 25 entries, I mean, each will be this. So I have distance vector entry. Each entry will be, I'm telling you the address of the network 1, the destination network, and subnet mask for network number 1, next hop distance. Okay, so I'm telling my neighbor the distance vector, and this is 1 entry, and I can have at most 25 entry in one packet. In one packet, at most 25 entry in this distance vector. And IP, because it uses Bellman 4 algorithm, so it has the problem of count to infinity. So it also put the 3 partial solution here. These are the 3 partial solutions we have described for the count to infinity problem. And here's an example routing table drawn from a router at CCU. Okay, so it has here are the destination networks, and it will tell you the next hop and the distance.